All right, today I'm going to go over with you guys your expectations for the calculations for the KC lab. Ultimately, your goal is to prove that K at a specific temperature is constant, or KC as it is. So you have done the lab, and you have actually done 4 different trials, and you had and then you had a 5th trial, which was your standard. So for purposes of demonstration, I'm going to be doing trial number 1. My trial number 1 had an absorbance of 0.15046, and the last cup, the darkest color that you had, was your standard, and my standard has an absorbance of 0.62302. Your job will be to do 4 different rice tables, 1 for each trial 1 through 4. So I expect to see 4 different rice tables and all these calcs done 4 separate times on your lab. So you're free to stop this video whenever you need to. If you want to, instead of using my data, you're welcome to plug in your data and just stop the video every time you want to do a different calc. But I'm going to take you through this step by step. So first off, what we need to do is to find K. So to do that, we'll need a rice table. We all know that a rice table requires the reaction. In this particular lab, you are adding 0.3 Fe plus 3 plus SCN minus, and that created that orange-looking complex called FeSCN 2+. So I'm actually going to spread these out a little bit to make it. I need a lot of room under I to show you how to do these calcs. Okay, so we're going to start with our initial concentrations. Now, it says on the bottles of that iron that you used and that thiocyanate that you used, they were 0.00 molar. However, when you mix the 2 together, you actually diluted them. So, since we diluted them, we're going to have to do a dilution calculation to find this initial concentration. So, we're going to do MV equals MV for each of these. So starting out, my initial molarity, let's look at iron, was 0.002. The amount of iron from your data table that you put into your trial number 1 was 5 mils. We want to know what is the molarity after the dilution, and if you count across your data table where you had the number of mils, it was a total of 10 milliliters that you did in the little cup. So that is going to be how we figure out the concentration initially of our iron plus 3. And that concentration for trial 1 turned out to be 0.001 molar. So that's our initial concentration of iron plus 3. So we're going to repeat this, and we're going to do the same thing for the thiocyanate. And our initial concentration is 0.002 as well. But we used 2 mils in our solution. We want to know the molarity if our total volume was 10 mils. And when you do that calculation, you get 4.00 times 10 to the negative 4th. My initial concentration of the complex is 0 because we didn't have any at the beginning. So now we can actually start our rice table. If we are going to find our K, we need all our equilibrium values, correct? So we do minus x plus x. And so we get 0.001 minus x, 4.00 times 10 to the negative 4th minus x, and x. So in order to find K, well, we need x, right? Oops. We need, not need, we need x. So how do we find x? This is going to be where our standard comes into play. So I'm going to switch to a new slide. We'll come back to this and fill in our x and do all our solving here momentarily. But I'm going to now talk about that standard a little bit and what was going on with that standard. So again, the reaction was iron plus 3 plus the thiocyanate gives us the FeSCN plus 2. All right, what we did in the standard, if you notice, we had a 0.2 molar compared to the original 0.002 molar of both. So the iron, if you notice, was 100 times more concentrated than the thiocyanate. What this is allowing us to assume, we're assuming that we are bombarding this thiocyanate so much that every single one of these becomes every single one of those. So that assumption is going to lead us to know that the concentration of this is equal to the concentration of the FeSN plus 2 at equilibrium. And the only way we can assure that is to bombard it with this really, really, really high concentration. So what we need to first figure out in order to do this calc is what is the concentration originally of this SCN minus? Well, we have to do a dilution again. If you look underneath your little milliliter data table, you see that we originally had that point. We're going to do another MV problem. That 0.002 times 2 mils is equal to the new molarity times a total of 20 mils. When we do that, we get an SCN minus concentration of 2 times 10 to the negative 4th. Okay, that then is equal to our concentration in our standard of the SCN at equilibrium. So what does this mean? Well, think back to the color. It was really, really, really dark, right? And it had that really, really, really high absorbance. It has the standard absorbance of 0.06233. Oh, sorry, not 0.06, 0.62303 is what my standard was. Your standard is going to be different, 0.62303. So how did this help me? I need the equilibrium concentration of FeSCN to find X, but not of the standard. I need it of trial 1, I need it again of trial 2, and I need it again of trial 3. So that's what I'm looking for. So how am I going to find this for trial 1, 2, 3, and 4? Well, I'm going to assume or apply what we call Beer's law. Beer's law is a law that says concentration is directly proportional to absorbance. So I'm going to do a proportion. If I know the absorbance of trial 1 and the standard, and I know the concentration of the standard, I can figure out the concentration of the trial by using the following equation. And this is found in the post lab if you can't see it. FeSCN plus 2 at equilibrium, and I'm going to write of your trial. This is what we're looking for. So this is going to be number 1, number 2, number 3, number 4, and so on, is equal to a proportion of the equilibrium absorbance of your trial divided by the equilibrium of the standard. So it's the same thing as saying this is to this as that is to that. So looking at this equation, all I'm going to do is, oh, and I got to multiply it, sorry, by the concentration of the FeSCN plus 2 standard, the dark stuff. So all I do is plug in. I'm going to plug in on top the absorbance of my trial 1, which I gave you at the beginning, to be 0.15046. And I'm going to divide that by my standard concentration. And I'm going to multiply that by the concentration of my standard. We just figured that out to be 2 times 10 to the negative 4th. So we're going to use this number in every single trial. We're going to use this number every single trial. This top number is going to vary for each trial. We have an absorbance for 1, 2, 3, and 4, so we'll get a different proportion, and this will be a different x. So when we multiply this out, we actually get this number to be 4.83 times 10 to the negative fifth. And that's our concentration at equilibrium for trial number 1. All right? That is my x. So now what I'm going to do, I'm going to go back to my table now that I know what x is, and I'm going to plug that x into every spot. Remember, this is 4.83 times 10 to the negative fifth. X is 4.83 times 10 to the negative fifth. And this is 4.83 times 10 to the negative fifth. So now I can do all my calcs. I can figure out, now I'll just go ahead and write it in blue. When I do the math here, I get 9.52 times 10 to the negative fourth for my concentration of iron, plus 3. I get 3.52 times 10 to the negative fourth for my concentration of the thiocyanate, and I get 4.83 times 10 to the negative fifth for my concentration of my iron thiocyanate complex. So to solve for K, I just do my unsubstituted expression, FeSCN plus 2 raised to the first divided by Fe plus 3 to the first times SCN minus to the first. And I plug everything in, and that would be 4.83 times 10 to the negative fifth divided by 9.52 times 10 to the negative fourth times, I lost my place, 3.52 times 10 to the negative fourth. And when I do the math, I end up getting a K, that's 144. So I believe the accepted K value was anywhere between, I think, 100 and 175 or something like that. But remember, I'm not looking at, is your K right? I'm looking at precision here. We're proving that K is constant. So I want, hopefully, all your Ks will be close to each other. And that's the important part. So really quick, one thing I want to do before I close up is to kind of verify what numbers are going to be different and what numbers are going to be the same when you're doing these. So this is one trial. You're going to have to do 3 more tables just like this. Your iron, since you used 5 mils in every single trial, is going to have the same initial concentration. So that number doesn't change. Okay? What number will change, I'll put in black. Black is changed, so we're going to have that number change. Obviously, your X is going to change. Your X changes because you're going to get a different proportion every time you multiply your standard absorption with the absorption of that trial. So how did we do that? Well, we're going to use a number that we figured out as the concentration of the standard at equilibrium, and that number was this. This number does not change. So you're always going to have this number multiplied by the proportion of absorbances. The standard always has the same absorption and concentration, so those two numbers stay the same. But what does change is your trial absorbance. Trial 1, 2, 3, 4 all have a different absorbance. So that number has to change, and that will cause us to have a different X for each trial. And that is how you do those calculations. Again, I want to see four rice tables with all your work shown and all your Ks. All right, good luck. Come see me if you have questions.